Tonight, we're going to do something ambitious. We're going to travel from where you're sitting right now all the way to the edge of the observable universe. And along the way, I'm going to show you something that might genuinely change how you see everything, the true scale of the cosmos. You've probably heard people say the universe is big. That's one of those statements that's technically true but completely inadequate. Saying the universe is big is like saying the ocean is damp or that fire is warm. It's such an understatement that it borders on meaningless. The universe isn't just big, it's so vast, so incomprehensibly enormous that the human mind wasn't designed to grasp it. Our brains evolved to understand the distance to the next river, the height of a tree, the size of a predator. We never needed to comprehend distances measured in trillions of miles. And yet, that's exactly what we're going to attempt tonight. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin our journey. Let's start with something you understand completely. The room you're in right now. Look around. Maybe you're in a bedroom, a living room, an office. The walls are probably somewhere between 10 and 30 feet away from you. This is a distance your brain handles effortlessly. You can estimate it by eye. You've walked across rooms like this thousands of times. You know exactly what this distance feels like. Now think about the building you're in. Maybe it's a house, an apartment building, an office complex. You know your way around. You can navigate from room to room without thinking about it. The whole structure might be 50 feet across, or 100, or several hundred if it's a large building. Still completely manageable, still within the realm of everyday experience. Step outside in your mind and consider your neighborhood. The streets you walk, the stores you visit, the homes of people you know. Maybe your daily world stretches a few miles in each direction. This is your territory, the geography that shapes your daily life. You know which roads get busy at rush hour, which shortcuts save time, where the good restaurants are. It's all mapped in your head, familiar and navigable. Your city or town extends this further. Maybe it's 10 miles across, maybe 50. You might not know every street, but you understand the general layout. Downtown is that direction. The suburbs spread out this way. The highway cuts through over there. These distances are still human-scaled. You can drive across town in half an hour or an hour. You've done it many times. Now, think about your country. If you're in the United States, you're looking at a nation roughly 3,000 miles from coast to coast. That's a serious distance. A road trip from New York to Los Angeles takes about 40 hours of driving, assuming you don't stop. Most people who make that journey spread it over several days, watching the landscape transform from eastern forests to midwestern plains to southwestern deserts to the Pacific coast. It's a long way, but it's still comprehensible. Millions of people make cross-country trips every year. It's challenging, but entirely achievable. The entire Earth has a circumference of about 25,000 miles at the equator. That's 8 times the distance from New York to Los Angeles. If you could drive around the entire planet on a road that followed the equator, it would take you about 350 hours of continuous driving. That's almost 15 days of non-stop motion. No breaks, no sleep, just driving. In practice, circumnavigating the Earth takes months if you're doing it by car and boat, or about 45 hours if you could book a continuous sequence of flights around the world. These are big distances, genuinely big, but they're still within the realm of human experience. People have walked around the world. People have sailed around the world. People have flown around the world. We have a sense of what the Earth's size means because we've explored all of it. We've mapped every continent, charted every ocean, climbed every mountain. The Earth is our home, and we know it well. But here's where things start to change. Here's where the numbers start to get strange. Because the Earth, as large as it seems when you're standing on its surface, is almost unimaginably small compared to what surrounds it. The first step on our journey outward takes us to something you can see almost every night. The Moon, Earth's only natural satellite, hanging in the sky like a faithful companion. It looks close, doesn't it? On a clear night, you can see details on its surface with your naked eye. The dark patches of the lunar seas, the bright rays of crater ejecta. With a pair of binoculars, you can see individual craters. It seems like you could almost reach out and touch it. But the Moon is about 239,000 miles away from Earth. Let me help you understand what that distance actually means. If you could somehow drive your car straight up into space at highway speeds, about 70 miles per hour, it would take you roughly 142 days to reach the Moon. That's nearly 5 months of continuous driving. No stops, no rest, just constant motion at speeds that would get you a ticket on most highways. 5 months to reach something that looks close enough to touch. When the Apollo astronauts traveled to the Moon between 1969 and 1972, they used the most powerful rockets ever built. The Saturn V rocket accelerated them to speeds of about 25,000 miles per hour. That's roughly 350 times faster than highway driving. And even at that incredible speed, it still took them about 3 days to reach the Moon. 3 days of traveling through empty space at speeds no human had ever experienced before. Here's something that might help you visualize this distance. If the Earth were the size of a basketball, the Moon would be about the size of a tennis ball, and it would be sitting about 24 feet away. That's the length of a typical living room. Not right next to the basketball, not orbiting close by, but all the way across the room. The space between Earth and Moon is vast enough that you could fit every other planet in our solar system in that gap with room to spare. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. All of them could line up between Earth and Moon. The Moon is the farthest place humans have ever traveled in person. Out of the roughly 100 billion humans who have ever lived, only 12 have walked on another world. And that other world, the Moon, is right next door in cosmic terms. It's practically touching us compared to the distances we're about to explore. When the astronauts walked on the Moon and spoke to mission control back on Earth, there was a communication delay of about 1.25 seconds each way. Radio signals travel at the speed of light, the fastest speed possible in the universe, and even light needs more than a second to cover the distance between Earth and Moon. You can hear this delay in the recordings. Every conversation has a pause, a lag, as words travel across nearly 250,000 miles of emptiness. Now let's jump to the center of our solar system. Our star, that blazing ball of hydrogen and helium that makes all life on Earth possible. Every morning it rises, every evening it sets, and we rarely think about just how far away it actually is. Our star is about 93 million miles from Earth. This distance is so important in astronomy that it has its own name. We call it 1 astronomical unit, or AU. It's the yardstick we use to measure distances within our solar system. But before we talk about that distance, let's appreciate what our star actually is. It contains about 99.8% of all the mass in our entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets, all of it together makes up less than 1/4 of 1% of the solar system's mass. Jupiter, the largest planet, is massive by any human standard, but our star could fit more than 1,000 Jupiters inside it. Our star is so large that you could line up about 109 Earths across its diameter. You could fit about 1,300,000 Earths inside its volume. Every second, it converts about 600 million tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to billions of nuclear bombs. And it's been doing this for about 4.5 billion years, and will continue for another 5 billion years before exhausting its fuel. At the stellar core, temperatures reach about 27 million degrees Fahrenheit. The pressure is so intense that hydrogen atoms are squeezed together until they fuse into helium, releasing energy in the process. This energy takes a remarkably long time to reach the surface. A photon created at the core might take anywhere from 10,000 to 170,000 years to bounce and scatter its way to the surface. But once it escapes into space, it takes only 8 minutes to reach Earth. 93 million miles. How do you even begin to understand a distance like that? Let's try some comparisons. If you could drive your car toward our star at highway speeds, it would take you roughly 150 years. You'd need to start driving when you were born and continue without stopping for your entire life, plus the lives of your children and most of your grandchildren's lives, just to get there. Obviously, you can't actually drive there, and it would vaporize your car long before you arrived, but the point is the distance itself. Light travels at about 186,000 miles per second. That's so fast that light could circle the entire Earth about 7.5 times in a single second. And yet, even light needs 8 minutes and 20 seconds to travel from our star to Earth. When you look at it directly, assuming you're doing it safely through proper filters, you're not seeing it as it is right now. You're seeing our star as it was 8 minutes and 20 seconds ago. If it suddenly went dark at this very moment, we wouldn't know for over 8 minutes. We'd still see it shining, still feel its warmth, completely unaware that anything had changed. This delay has practical implications that most people never consider. Solar flares, massive eruptions on the stellar surface that can interfere with satellites and power grids, travel much slower than light. We can see them happening in real time, and then we have a warning period, usually a day or two, before the charged particles arrive at Earth. But we're still seeing the flare as it was 8 minutes ago. The information is already old when it reaches us. Mercury, the closest planet to our star, orbits at an average distance of about 36 million miles. That's still an enormous distance, more than 150 times the distance from Earth to the Moon. Mercury completes an orbit every 88 Earth days, racing through space at over 100,000 miles per hour, the fastest of any planet in our solar system. Venus, our closest planetary neighbor, comes within about 25 million miles of Earth when the two planets are on the same side of their orbits. That's still more than 100 times the distance to the Moon. Venus is similar to Earth in size and mass, which is why it's sometimes called Earth's twin. But its surface temperature is hot enough to melt lead, and its atmosphere is thick with sulfuric acid clouds. It's a vision of what Earth might have become, with a slightly different history. Venus rotates backward compared to most planets, and so slowly that a day on Venus lasts longer than a year on Venus. If you could somehow stand on its surface, which you couldn't because you'd be crushed by the pressure and vaporized by the heat, you'd experience a day lasting about 243 Earth days. The atmosphere is so thick, about 90 times denser than Earth's, that the surface pressure is similar to what you'd experience half a mile deep in Earth's oceans. Mars, the planet that has captured human imagination more than any other, varies in distance from Earth between about 34 million miles when we're closest, and 250 million miles when we're on opposite sides of our orbits. This variable distance affects everything about Mars exploration. Launch windows to Mars only open every 26 months or so when the planets are positioned favorably. Miss your window and you have to wait more than 2 years for the next opportunity. Mars is a cold, dry world today, but billions of years ago it had liquid water on its surface. Rivers carved channels into its terrain, lakes pooled in craters. An ocean may have covered much of its northern hemisphere. The evidence is written in the rocks and landforms that our rovers have photographed and studied. Mars lost its water because it lost its magnetic field, which allowed the solar wind to strip away its atmosphere over billions of years. Without a thick atmosphere to trap heat and maintain pressure, the water evaporated and was lost to space. When NASA operates rovers on Mars, like Curiosity and Perseverance, there's always a communication delay. At the closest approach, signals take about 3 minutes to travel each way. At the farthest distance, the delay is over 20 minutes each way. This means you can't drive a Mars rover in real time, like a remote-controlled car. You have to plan every movement carefully, send commands, wait for confirmation, and hope nothing goes wrong while you're waiting. If the rover gets stuck or encounters a problem, you might not know about it for over 40 minutes. The Perseverance rover, which landed in February of 2021, is searching for signs of ancient microbial life in a crater that was once a lake. It's also collecting rock samples that a future mission will retrieve and return to Earth. These samples will be the first material from another planet ever brought back to our laboratories for study. If we find evidence of life in those samples, it will be one of the most significant discoveries in human history. Beyond Mars, we enter the realm of the giant planets. Worlds so large they make Earth look like a marble next to bowling balls. Jupiter, the largest planet in our solar system, is about 484 million miles from our star on average. When Jupiter and Earth are on the same side of their orbits, the distance between them shrinks to about 365 million miles. When we're on opposite sides, it stretches to over 600 million miles. Jupiter is massive. More than 1,300 Earths could fit inside it. Its Great Red Spot, a storm that has been raging for at least 350 years and possibly much longer, is so large that you could fit the entire Earth inside it with room to spare. This storm has winds reaching 400 miles per hour at its edges. It's been shrinking in recent decades, and astronomers aren't sure why or whether it will eventually disappear entirely. Jupiter spins so fast that it completes a rotation in just under 10 hours. This rapid rotation causes the planet to bulge at its equator. It also generates the most powerful magnetic field of any planet in our solar system, about 20,000 times stronger than Earth's. This magnetic field traps charged particles in radiation belts so intense that they would be lethal to unprotected humans. Jupiter has at least 95 known moons, including 4 large ones discovered by Galileo back in 1610, when he first pointed his homemade telescope at the planet. These Galilean moons are worlds in their own right. Io, the innermost, is the most volcanically active body in the solar system. Its surface is constantly being reshaped by eruptions that can shoot material hundreds of miles into space. The volcanic activity is powered by tidal heating, as Jupiter's enormous gravity flexes and squeezes the moon. Europa, Another of the Galilean moons has a liquid water ocean beneath its icy surface that contains more water than all the oceans on Earth combined. The ice shell is probably about 10 to 15 miles thick, and the ocean beneath might be 60 miles deep. This ocean is in contact with the moon's rocky mantle, which means there could be hydrothermal vents like the ones on Earth's ocean floor that support life without sunlight. Europa is one of the most promising places to search for extraterrestrial life in our solar system. Ganymede is the largest moon in the solar system, bigger even than the planet Mercury. It's the only moon known to have its own magnetic field generated by a liquid iron core. Callisto, the outermost of the four, has one of the most heavily cratered surfaces in the solar system, a record of impacts stretching back billions of years. When the Voyager spacecraft flew past Jupiter in 1979, the signal delay was about 40 minutes each way. Every command sent from Earth took 40 minutes to arrive. Every photo taken by the spacecraft took 40 minutes to reach the scientists waiting on the ground. The spacecraft had to be smart enough to operate autonomously, making decisions on its own, because waiting for instructions from Earth wasn't practical at these distances. Saturn, famous for its stunning ring system, orbits at about 890 million miles from our star. That's nearly twice Jupiter's distance. Light takes about 80 minutes to reach Saturn from here. When the Cassini spacecraft orbited Saturn from 2004 to 2017, taking extraordinary close-up photos of the planet and its moons, the communication delay was over an hour each way. Scientists on Earth would send commands and then wait more than 2 hours to see the results. Saturn's rings are made mostly of ice particles, ranging from tiny grains to chunks the size of houses. The rings are enormous in extent, stretching nearly 50,000 miles from the planet's cloud tops, but they're remarkably thin. In most places, the rings are only about 30 feet thick. If you scaled Saturn down to the size of a basketball, its rings would be thinner than a sheet of paper. The rings are also surprisingly young by cosmic standards, probably only about 100 million years old. Dinosaurs may have looked up at a Saturn without rings. Saturn has at least 146 known moons, more than any other planet in our solar system. Titan, the largest, is bigger than Mercury and has a thick atmosphere denser than Earth's. It's the only moon in our solar system with a substantial atmosphere, and it's the only place besides Earth known to have liquid lakes on its surface. But those lakes aren't filled with water. They're filled with liquid methane and ethane. If you could visit Titan, you'd see orange skies and hydrocarbon rain falling into lakes and seas. Enceladus, one of Saturn's smaller moons, has geysers at its south pole that spray water ice into space. The Cassini spacecraft flew through these plumes and detected complex organic molecules, hydrogen gas, and other chemicals that suggest a liquid water ocean beneath the ice, kept warm by tidal heating. Like Europa, Enceladus is now considered a prime candidate for finding life beyond Earth. Uranus and Neptune, the ice giants, are even more remote. Uranus orbits at about 1.8 billion miles out. Neptune, the most distant planet, averages about 2.8 billion miles from our star. These worlds are so far that our star appears as just a very bright point in their skies, providing light but very little warmth. Uranus is unique in the solar system because it rotates on its side. Its axis is tilted about 98 degrees, so it essentially rolls around its orbit rather than spinning upright like the other planets. This means that for part of its 84-year orbit, one pole points sunward for decades at a time. No one knows for certain what caused this extreme tilt, but the leading theory is that a massive object, perhaps Earth-sized, collided with Uranus billions of years ago and knocked it over. Neptune, the windiest planet in our solar system, has storms with wind speeds exceeding 1,200 miles per hour. When Voyager 2 flew past in 1989, it photographed a giant storm called the Great Dark Spot, similar in appearance to Jupiter's Great Red Spot. But when the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot was gone, and a new storm had appeared in a different location. Neptune's atmosphere is dynamic and changeable, despite the planet's distance from our star and the weak sunlight it receives. Voyager 2 is the only spacecraft to have visited both Uranus and Neptune. It flew past Uranus in 1986, 9 years after launch, and past Neptune in 1989. At Neptune, the signal delay was over 4 hours each way. A full conversation between the spacecraft and Earth, sending a question and receiving an answer, would have taken over 8 hours. After passing Neptune, Voyager 2 continued into the outer solar system, following Voyager 1 into interstellar space. Both spacecraft are still transmitting data, their signals growing weaker as they travel farther from us. They're the most distant human-made objects, ambassadors carrying golden records with sounds and images from Earth, messages in bottles cast into the cosmic ocean. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies including dwarf planets like Pluto and Eris. Pluto, which was considered the 9th planet until 2006, orbits at an average distance of about 3.7 billion miles from our star. At its farthest point, Pluto swings out to nearly 4.6 billion miles. When the New Horizons spacecraft flew past Pluto in July of 2015, it was so far from Earth that light took over 4.5 hours to make the journey. The spacecraft had been traveling for 9.5 years just to reach Pluto. 9.5 years of constant motion through the void of space, and Pluto is still considered part of our solar system's inner regions compared to what lies beyond. The photos New Horizons sent back revealed a world far more complex and interesting than anyone expected. Mountains of water, ice, nitrogen glaciers, a thin atmosphere, and a heart-shaped plain that captured the public imagination. But all that data took months to transmit back to Earth because of the enormous distance and the limited power of the spacecraft's transmitter. Beyond the Kuiper Belt lies the Oort cloud, a spherical shell of icy bodies that marks the true outer boundary of our star's gravitational influence. The Oort cloud extends from about 2,000 AU to perhaps 100,000 AU outward. In miles, that's roughly 9.3 trillion miles at its outer edge. Consider Voyager 1, humanity's most distant spacecraft. It launched in 1977 and has been traveling outward at over 38,000 miles per hour ever since. After nearly 50 years of continuous flight, it has covered roughly 15 billion miles. That sounds impressive until you realize it's completed only about 1/6 of the journey to the outer Oort cloud. If Voyager 1 keeps going, it won't reach the inner Oort cloud for another 300 years. It won't exit the outer Oort cloud for 30,000 years. Our fastest messenger to the stars will spend longer crossing our own solar system's backyard than human civilization has existed. And here's the thing that might really surprise you. Even the outer Oort cloud, that unimaginably distant boundary of our solar system, is still incredibly close compared to the nearest star. We're about to discover just how isolated we really are. The nearest star to us is Proxima Centauri, a small red dwarf in the Alpha Centauri system. It's our closest stellar neighbor, the nearest sun beyond our own, and it's about 25 trillion miles away. Let me write that out so you can see it. 25 followed by 12 zeros. 25 million miles. At this point, miles become almost useless as a unit of measurement. The numbers are so large that they stop meaning anything to our human brains. That's why astronomers use a different unit when talking about interstellar distances. The light year. A light year is the distance light travels in 1 year, moving at 186,000 miles per second for an entire year. It works out to about 5.88 trillion miles. Proxima Centauri is about 4.24 light years away. That sounds more manageable, doesn't it? Just 4.25 of these units. But remember what a light year represents. Light, the fastest thing in the universe, traveling at a speed so great it could circle Earth 7.5 times per second, still needs 4 years and 3 months to reach Proxima Centauri. Let me try to help you grasp this distance with some comparisons. Here's a way to feel this distance. When you look at Proxima Centauri tonight, assuming you're in the southern hemisphere where it's visible, the photons entering your eye left that star over 4 years ago. Whatever is happening on Proxima Centauri right now, we won't know about it until 2029 or later. If someone on a planet there pointed a telescope at Earth today, they'd see our world as it was during 2021, before many current events had even occurred. The present moment is an illusion across interstellar distances. We're all living in each other's past. Even at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe at its peak speed of about 430,000 miles per hour, it would take over 6,000 years to reach Proxima Centauri. You could have started your journey when the ancient Egyptians were building the first pyramids, and you still wouldn't have arrived yet. You'd still be traveling, still coasting through the emptiness between stars, still thousands of years from your destination. Here's another way to think about it. The space between Earth and the Moon is about 239,000 miles. You could fit about 105 million moon distances between us and Proxima Centauri. If you laid out that many quarter-mile laps on a running track, you'd have enough track to run to the nearest star. The Alpha Centauri system, which includes Proxima Centauri, is actually a triple star system. Alpha Centauri A and Alpha Centauri B are 2 solar-type stars orbiting each other every 79 years. They're close enough together that to the naked eye they appear as a single bright star in the southern sky. Proxima Centauri is a much smaller, dimmer red dwarf that orbits the pair at a distance of about 13,000 times the Earth to star distance. It takes Proxima Centauri about 550,000 years to complete one orbit around its companions. In 2016, astronomers discovered a planet orbiting Proxima Centauri in its habitable zone, where temperatures might allow liquid water to exist on the surface. This planet, Proxima Centauri b, is only slightly more massive than Earth. It's the closest known potentially habitable planet to our solar system. If we ever develop the technology to send probes or people to another star, this is likely where we'd go first. But even close is misleading when we're talking about interstellar distances. Voyager 1, which has been traveling through space since 1977, is currently about 15 billion miles from Earth. That sounds like a lot, and it is. It's beyond the heliosphere, the bubble of charged particles that our star creates around itself. Voyager 1 is officially in interstellar space, but it's only traveled about 0.025% of the distance to Proxima Centauri. After nearly 50 years of flight, it's completed less than 1/40th of 1% of the journey to the nearest star. If our star were the size of a grain of sand about a millimeter across, Proxima Centauri would be another grain of sand located about 4.5 miles away. 2 tiny grains of sand separated by miles of empty space. the space between stars is almost incomprehensibly empty. If you could compress all the matter in the universe to the same density as Earth, the universe would only be about a light year across. Most of space is emptiness. The atoms that make up planets and stars and people are tiny specks in vast oceans of nothing. When you look up at the night sky, you're seeing points of light separated by light years of vacuum, by emptiness so complete that the average density of the universe is only about 6 hydrogen atoms per cubic meter. Before we continue our journey outward, let's talk about what stars actually are and how they differ from each other. Stars are giant balls of gas, mostly hydrogen and helium, held together by gravity and powered by nuclear fusion in their cores. The heat and pressure at the center of a star are so intense that hydrogen atoms are forced together to form helium, releasing enormous amounts of energy in the process. This energy works its way outward and radiates into space as light and heat. But not all stars are created equal. They come in a wide range of sizes, temperatures, and colors. Red dwarf stars are the smallest and coolest stars that still qualify as stars. They're typically less than half the mass of our star and can be as small as 8% of that mass. Below that limit, there's not enough pressure at the core to sustain hydrogen fusion, and you get a brown dwarf instead, a failed star that glows dimly from residual heat but doesn't truly shine. Red dwarfs are incredibly common. About 70% of all stars in our galaxy are red dwarfs, but they're so dim that none of them are visible to the naked eye from Earth, despite being the most numerous stars around. Proxima Centauri is a red dwarf. So is Barnard's star. These tiny, cool stars burn their fuel so slowly that they can shine for trillions of years. Our star will exhaust its hydrogen in about 5 billion years, but red dwarfs will still be shining long after the last solar-type star has died. Yellow dwarf stars, like ours, are medium-sized stars with surface temperatures around 10,000 degrees Fahrenheit. They're less common than red dwarfs, but more common than larger stars. Our star is actually classified as a G-type main sequence star, which puts it in the middle of the stellar population. There's nothing particularly special about it from an astronomical perspective. It's a fairly ordinary star. Not too hot, not too cool, not too big, not too small. Blue giant and supergiant stars are the largest and hottest stars in the universe. They can be dozens or even hundreds of times the mass of our star, with surface temperatures of 50,000 degrees Fahrenheit or more. These stars burn through their fuel rapidly, living fast and dying young. While red dwarfs last for trillions of years, blue supergiants might last only a few million years before exploding as supernovae. Betelgeuse, the bright red star in the constellation Orion, is a red supergiant near the end of its life. It's about 700 times the diameter of our star. If you placed Betelgeuse at the center of our solar system, it would engulf the orbits of Mercury, Venus, Earth, and Mars, and extend past the asteroid belt. Betelgeuse will explode as a supernova sometime in the next 100,000 years, and when it does, it will be visible from Earth during the day. When massive stars die, they leave behind exotic remnants. Neutron stars are the collapsed cores of stars that were between about 8 and 25 times the mass of our star. The core collapses so violently that protons and electrons are squeezed together to form neutrons. A neutron star might be only 12 miles across, but contain more mass than our entire star does. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. Black holes form from the deaths of the most massive stars, those more than about 25 times the mass of our star. When these giants collapse, nothing can stop the infall. The matter is crushed into a point of infinite density called a singularity, surrounded by an event horizon from which nothing, not even light, can escape. Black holes are invisible by definition, but we can detect them by their effects on nearby matter and light. Within about 20 light-years of Earth, there are roughly 130 known star systems. Some are single stars like ours. Others are binary systems, two stars orbiting each other in a gravitational dance. A few are triple systems or even more complex arrangements. Barnard's star is the second closest star system to Earth, about 6 light-years away. It's a tiny red dwarf, far smaller and dimmer than our star. What makes it interesting is its motion. Barnard's star is moving toward our solar system faster than any other star, about 90 miles per second relative to us. In about 10,000 years, it will be closer to us than Proxima Centauri is now. But even then, even at its closest approach, it will still be nearly 4 light-years away. Stellar distances are so vast that even stars moving at tremendous speeds take millennia to change their positions significantly. Sirius, the brightest star in the night sky, is about 8.6 light-years away. When you look at Sirius tonight, you're seeing light that left that star about 8.5 years ago. If you're 25 years old, you're seeing Sirius as it was when you were a teenager, probably in high school. The Sirius you see tonight is Sirius from the past, not Sirius as it exists right now. Sirius is actually a binary system. The bright star we see, Sirius A, has a companion called Sirius B, a white dwarf. White dwarfs are the collapsed remnants of stars that have exhausted their nuclear fuel. Sirius B is about the size of Earth, but has nearly the mass of our star. The material is so compressed that a teaspoon of it would weigh about 5 tons on Earth. The two stars orbit each other every 50 years, locked together by gravity across the void. Vega is another bright star, about 25 light-years away. If you're 25 years old and you look at Vega tonight, you're seeing light that left that star the year you were born. When that light began its journey toward Earth, you didn't exist yet. Your parents might have been looking up at that same star, seeing light that left 25 years before that. The Vega we see tonight is a younger Vega, showing us what that star looked like a quarter century ago. This connection between distance and time is one of the most profound aspects of astronomy. Because light takes time to travel, every time we look at a distant object, we're looking into the past. The farther something is, the further back in time we're seeing. The night sky is a time machine, showing us not how the universe is, but how the universe was. As we continue our journey outward, we start to encounter objects that are not individual stars, but vast collections of stars, clusters, nebulae, and eventually galaxies. The Orion Nebula is one of the most famous objects in the night sky, visible as a fuzzy patch in the sword of the constellation Orion. It's about 1,344 light-years away. This means the light reaching your eyes tonight left the nebula when the Roman Empire was still around, when Charlemagne was being crowned Emperor of the Romans, when the concept of a unified Europe was first being imagined. The Orion Nebula is a stellar nursery, a vast cloud of gas and dust where new stars are being born. It's about 24 light-years across, large enough that you could line up thousands of solar systems inside it. Within the nebula, gravity is pulling clumps of gas together, heating them up, eventually igniting nuclear fusion and creating new stars. Some of the stars visible in the nebula are only a few 100,000 years old, cosmic infants compared to our 4.5 billion-year-old star. The Pleiades, also known as the Seven Sisters, is an open star cluster about 444 light-years away. When the light we see from the Pleiades tonight started its journey, Christopher Columbus hadn't yet sailed to the Americas. Leonardo da Vinci was a young man just beginning his artistic career. The Renaissance was in full swing, and the modern world was only beginning to take shape. That light has been traveling through space all this time, crossing nearly 3 trillion miles just to reach your eyes tonight. The Crab Nebula is the remnant of a supernova, a massive stellar explosion that was observed on Earth in the year 1054. Chinese astronomers recorded a guest star that appeared suddenly in the sky and was bright enough to be visible during the day for 23 days. What they were seeing was a star dying, exploding with such force that it briefly outshone everything else in its galaxy. The Crab Nebula is about 6,500 light-years away. The star that created it actually exploded about 6,500 years before 1054, but the light from that explosion took all that time to reach Earth. At the center of the Crab Nebula is a pulsar, a rapidly rotating neutron star about 12 miles across, but containing more mass than our star does. It spins about 30 times per second, sending beams of radiation sweeping through space like a lighthouse beam. This tiny remnant of a once massive star is one of the most extreme objects in the universe, its density so great that a teaspoon of neutron star material would weigh about 6 billion tons on Earth. Now we need to zoom out even further to see the structure we're embedded in. Our galaxy, the Milky Way. On a dark night, far from city lights, you can see the Milky Way as a pale band of light stretching across the sky. This is the combined glow of hundreds of billions of stars, so numerous and so distant that they blur together into a luminous river. When you look at the Milky Way, you're looking through the disk of our galaxy, seeing more stars in your line of sight than you could ever hope to count. The word galaxy comes from the Greek word for milk, galaxias, which is where the Milky Way gets its name. Ancient people looked up and saw this river of light and imagined it as milk spilled across the heavens by the gods. They had no way of knowing what it really was. It wasn't until Galileo pointed his telescope at the Milky Way in 1610 that anyone realized it was made of countless individual stars, far too faint and far too numerous to see individually with the naked eye. The Milky Way is a barred spiral galaxy about 100,000 light-years across. Let me help you understand what that means. If you could somehow travel at the speed of light, moving at 186,000 miles per second, it would take you 100,000 years to cross from one side of our galaxy to the other. Light that left one edge of the Milky Way when modern humans were first leaving Africa would just now be arriving at the far edge. That's how big our galaxy is. A barred spiral galaxy has a central bulge of older stars, with a bar-shaped structure running through it. From this bar, spiral arms wind outward, containing younger stars, gas, and dust. If you could see the Milky Way from above, it would look something like a pinwheel with bright arms spiraling out from a glowing center. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is uncertain because we're inside the galaxy, like trying to count all the trees in a forest while standing in the middle of it. Dust blocks our view in many directions. Dim stars are hard to detect, but the best estimates suggest around 200 to 300 billion stars in our galaxy alone. If you could count one star per second without ever stopping to sleep or eat or do anything else, it would take you over 8,000 years to count all the stars in our galaxy. And that's just one galaxy among trillions in the observable universe. Our star is located in one of the spiral arms, about 26,000 light-years from the galactic center. We're in what's called the Orion Arm, or sometimes the Orion Spur, a relatively minor arm between the larger Sagittarius Arm and the Perseus Arm. When you look toward the constellation Sagittarius, you're looking toward the heart of the Milky Way, toward a region so dense with stars and gas and dust that it glows with the combined light of billions of suns. At the very center of our galaxy lurks something extraordinary, a supermassive black hole called Sagittarius A star. It contains the mass of about 4 million suns crammed into a region smaller than Mercury's orbit. Black holes are one of the strangest predictions of Einstein's theory of general relativity, and for decades many physicists thought they might be mathematical curiosities that don't exist in the real universe. But observations over the past few decades have confirmed that black holes are not only real, they're common. Stellar black holes, formed from the deaths of massive stars, are scattered throughout the galaxy. And at the centers of most large galaxies, including our own, supermassive black holes sit like cosmic drains, influencing everything around them. Sagittarius A star was first detected in 1974 as a source of strong radio emissions coming from the direction of the galactic center. For decades, astronomers studied the stars orbiting around this invisible object, measuring their speeds and paths with ever-increasing precision. Some of these stars orbit so close to the black hole that they complete their orbits in just a few years, moving at speeds of thousands of miles per second. In 2020, physicists Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize for their work measuring these stellar orbits and proving beyond reasonable doubt that a supermassive black hole exists at the center of our galaxy. And in 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, showing the shadow of the black hole against the glowing ring of superheated gas around it. The black hole itself is invisible, of course. Black holes are defined by their event horizons, the boundary beyond which nothing can escape, not even light. But the gas falling toward the black hole gets compressed and heated to millions of degrees, glowing brightly before it crosses the event horizon and disappears forever. This glowing ring surrounding a dark shadow is what the Event Horizon Telescope captured. Despite its immense mass, Sagittarius A star is relatively quiet as supermassive black holes go. It's not actively consuming large amounts of material and isn't producing the powerful jets of energy seen in some other galaxies. But it hasn't always been so calm. Evidence suggests that millions of years ago, Sagittarius A star had a more active period, and it could become active again if enough gas or even an unlucky star falls too close. The light we receive from stars near the galactic center left those stars 26,000 years ago. When that light began its journey, humans were living in the Ice Age. We were using stone tools. We were hunting woolly mammoths and giant ground sloths. Agriculture hadn't been invented. There were no permanent settlements, no cities, no nations. Everything we think of as civilization has happened while light from the galactic center was traveling toward us. Our star orbits the galactic center at about 500,000 miles per hour. That sounds incredibly fast, and it is by human standards. At that speed, you could travel from New York to Los Angeles in about 19 seconds. But the galaxy is so vast that even at this tremendous velocity, it takes about 230 million years to complete a single orbit. The last time our star was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. They would rise to dominance, rule the planet for over 160 million years, go extinct 66 million years ago, and mammals would eventually take over and produce humans, all during a single orbit around the galaxy. Scientists call this period one orbit around the galaxy, a galactic year. Earth is about 20 galactic years old. Our star has completed about 20 orbits since it formed. In that time, the entire history of our solar system has unfolded, from the formation of the planets, to the emergence of life, to the evolution of humans. And from a galactic perspective, that's barely any time at all. Now we're going to do something that puts everything so far into perspective. We're going to leave our galaxy entirely and look at what lies beyond. The nearest major galaxy to the Milky Way is the Andromeda Galaxy, also known as Messier 31. On a clear, dark night, you can see it with your naked eye as a faint, fuzzy patch of light in the constellation Andromeda. It looks small and distant, but it's actually the most distant object you can see without a telescope. The Andromeda Galaxy is about 2.5 million light-years away, 2.5 million light-years. The light entering your eyes when you look at Andromeda tonight started its journey when early human ancestors were just beginning to use stone tools in Africa. Homo habilis was emerging, the first members of the genus Homo, and they would have no way of knowing that the faint light, leaving a distant island of stars, would one day reach the eyes of their descendants standing on a planet millions of years in the future. To feel this distance, consider this. If you could blink once for every year since the Big Bang, you'd blink about 14 billion times. That's every year the universe has existed, one blink at a time. Now imagine trying to cross the distance to Andromeda at the speed of light, blinking once per year as you travel. You'd blink 2.5 million times before you arrived. Even at the fastest speed physics allows, the journey would take longer than the entire span of human evolution. Andromeda is larger than the Milky Way, containing perhaps 1 trillion stars compared to our few hundred billion. It spans about 220,000 light-years across, more than twice the diameter of our galaxy. If our eyes were sensitive enough to see its full extent in the night sky, Andromeda would appear about 6 times wider than the full moon. It's enormous, but it's so far away that we only see the bright central bulge with our naked eyes. Andromeda, like the Milky Way, has a supermassive black hole at its center. Andromeda's black hole is even more massive than ours, weighing in at about 100 million solar masses compared to the Milky Way's 4 million. This monster sits quietly at the heart of our nearest large neighbor, influencing the motion of stars for thousands of light-years around it. Here's something remarkable. The Andromeda Galaxy is moving toward us at about 250,000 miles per hour. In about 4.5 billion years, it will collide with the Milky Way. The two galaxies will merge over hundreds of millions of years, their stars swirling together in a cosmic dance, eventually forming a single giant elliptical galaxy that astronomers have already nicknamed Milkdromeda, or sometimes Milkomeda. But don't worry about the collision. Despite the word collision, individual stars are so far apart that actual impacts between stars will be extremely rare. Remember our grain of sand analogy, where stars are like grains of sand separated by miles of empty space? When the two galaxies pass through each other, it's less like two cars crashing and more like two swarms of bees passing through each other. The stars will be scattered and reorganized by gravitational effects, but the vast empty spaces between them will remain empty. Life on Earth, if it still exists by then, probably won't even notice the collision directly. The night sky will gradually change over millions of years as the two galaxies blend together, but there won't be any sudden catastrophe. Between the Milky Way and Andromeda lies a vast emptiness, over 2 million light-years of almost nothing. A few dwarf galaxies drift through this space, small collections of millions or billions of stars. But compared to the great spirals, they're barely a speck. Most of intergalactic space is vacuum, emptier than anything we can create in laboratories on Earth, with perhaps 1 atom per cubic meter on average. The Milky Way and Andromeda are the 2 largest members of the local group, a collection of more than 80 galaxies bound together by gravity. The local group spans about 10 million light-years. Other members include the Triangulum galaxy, a spiral galaxy about 3 million light-years away, and dozens of smaller dwarf galaxies, some of which are actually orbiting the Milky Way like moons orbiting a planet. The Large and Small Magellanic Clouds are 2 dwarf galaxies visible from the southern hemisphere. They're actually satellite galaxies of the Milky Way, gravitationally bound to us and eventually destined to merge with our galaxy over the next several billion years. The Large Magellanic Cloud is about 160,000 light-years away. When you look at it from a dark location in the southern hemisphere, you're seeing light that left during the Ice Age, when mammoths roamed the northern continents. Beyond the local group, the universe reveals its true structure. Galaxies aren't scattered randomly through space. They're organized into a vast web of filaments and walls, surrounding enormous voids where almost nothing exists. Galaxy clusters are collections of hundreds or thousands of galaxies bound together by gravity. The Virgo cluster, about 54 million light-years away, contains more than 2,000 galaxies. It's so massive that its gravity affects everything around it, including our own local group. The local group is not floating alone in space. It's part of a larger structure called the Virgo supercluster, a collection of galaxy groups and clusters stretching across roughly 110 million light-years. At the heart of the Virgo supercluster is the Virgo cluster, a massive collection of more than 2,000 galaxies located about 54 million light-years from Earth. When the light we see from the Virgo cluster tonight started its journey, dinosaurs had been extinct for about 12 million years. But the first true primates were just beginning to appear. Our distant ancestors were small, shrew-like creatures climbing through tropical forests, and they would have no idea that the light leaving distant galaxies would one day reach the eyes of their descendants. The Virgo cluster is dominated by several giant elliptical galaxies, including Messier 87, one of the most massive galaxies known. Messier 87 contains several trillion stars and has a supermassive black hole at its center, weighing about 6.5 billion solar masses. That's more than 1,000 times the mass of the black hole at the center of our Milky Way. In 2019, the Event Horizon Telescope released the first image ever taken of a black hole, and it was this monster in Messier 87, not our own Sagittarius A star. The image showed a glowing ring of superheated gas surrounding a dark shadow, the event horizon itself, the point of no return for anything that crosses it. The Virgo cluster is so massive that it exerts a gravitational pull on everything around it, including our local group. Despite the overall expansion of the universe, which we'll discuss shortly, the local group is actually falling toward the Virgo cluster at about 250 miles per second. We'll never actually reach it because the distance is too vast and the universe's expansion is accelerating. But the gravitational attraction is measurable and real. Beyond the Virgo supercluster, we find even larger structures. The Laniakea supercluster, identified in 2014, is a vast structure containing about 100,000 galaxies spread across 520 million light-years. The Milky Way is located in the outer reaches of Laniakea, which translates to immense heaven in Hawaiian. The name was chosen to honor Polynesian navigators who used their knowledge of the heavens to explore the Pacific Ocean. Laniakea was discovered by a team of astronomers led by Brent Tully, who mapped the motions of galaxies throughout our region of the universe. They found that all the galaxies in our corner of the cosmos are flowing toward a common point called the Great Attractor, a region of enhanced gravitational pull hidden behind the disk of our own galaxy. We can't see the Great Attractor directly because the Milky Way's dust and stars block our view in that direction, but we can detect its influence on the motion of galaxies around us. But even Laniakea is not the largest structure in the universe. Galaxy superclusters are organized into even larger structures called filaments. These are vast threads of galaxies stretching hundreds of millions of light years through space, surrounding enormous empty regions called voids. The cosmic web, as this structure is called, looks almost like a sponge on the largest scales, with matter concentrated into thin walls and filaments surrounding mostly empty bubbles. The Hercules Corona Borealis Great Wall, discovered in 2013, is one of the largest known structures in the universe. It's about 10 billion light-years long, roughly 1/9 the diameter of the observable universe. It took light 10 billion years to cross this structure. When that light started its journey, our star and Earth didn't exist yet. Our solar system wouldn't form for another 5.5 billion years. The early universe was a very different place, younger, denser, filled with galaxies that were still forming and evolving. Cosmic voids are even stranger than the filaments. These are regions of space, often hundreds of millions of light-years across, that contain almost no galaxies at all. The Boots void, discovered in 1981, is about 330 million light-years in diameter and contains far fewer galaxies than would be expected for a region that size. If the Milky Way were at the center of the Boots void, we would have thought until the 1960s that the universe consisted of nothing but the Milky Way, because no other galaxies would be visible without extremely powerful telescopes. The existence of cosmic voids and filaments tells us something profound about the early universe. The cosmic web isn't random. It's the result of tiny density variations in the early universe, fluctuations in the distribution of matter that existed just after the Big Bang. Regions that were slightly denser than average attracted more matter through gravity and eventually became the filaments and clusters we see today. Regions that were slightly less dense lost matter to their neighbors and became the voids. The structure we see today is the fossil imprint of those primordial fluctuations, preserved and amplified over billions of years of cosmic evolution. At this point, we need to talk about something that fundamentally changes how we understand cosmic distances. The universe is expanding. In 1929, astronomer Edwin Hubble made one of the most important discoveries in the history of science. He noticed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This isn't because galaxies are flying through space away from us. It's because space itself is expanding, stretching out, carrying galaxies along with it. Think of it like raisins in a loaf of bread that's rising. The raisins aren't moving through the dough, but as the dough expands, the raisins get farther apart from each other. A raisin on one side of the loaf sees all the other raisins moving away from it, and the ones farther away appear to be moving faster because there's more dough between them to expand. This expansion has a profound implication. If space is expanding now, then in the past, everything was closer together. Run the clock backward far enough, and you reach a point when all the matter and energy in the universe was concentrated into an incredibly hot, dense state. This is the Big Bang, the beginning of the universe as we know it, about 13.8 billion years ago. The expansion of space also means that very distant objects are receding from us incredibly fast. So fast, in fact, that the light from some objects will never reach us, no matter how long we wait. There's a cosmic horizon, a boundary beyond which we cannot see and will never be able to see, because the expansion of space is carrying those regions away faster than light can travel toward us. This might sound like it violates the rule that nothing can travel faster than light, but it doesn't. The galaxies themselves aren't moving through space faster than light. Space itself is expanding, and there's no speed limit on how fast space can expand. It's a subtle but crucial distinction. The galaxies are sitting relatively still in their local regions of space, but the space between us and them is stretching faster than light can cross it. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's not the entire universe, which might be infinite for all we know. It's just the part we can observe, the part within our cosmic horizon. The observable universe has a radius of about 46 billion light-years. Wait a minute, you might be thinking, if the universe is only 13.8 billion years old, how can we see objects 46 billion light-years away? Light hasn't had time to travel that far. The answer is the expansion of space. When light left those distant objects billions of years ago, they were much closer to us. But while the light was traveling toward us, space was expanding, carrying both us and those objects farther apart. The light eventually reaches us, but the objects that emitted it are now much farther away than they were when the light left them. Think of it like this. Imagine you're walking on a rubber sheet and someone at the other end of the sheet throws a ball toward you. While the ball is in the air, someone stretches the rubber sheet, making it longer. The ball eventually reaches you. But the person who threw it is now much farther away than when they threw it. The ball didn't have to travel the entire stretched distance. It only had to travel through the space that existed while it was in motion. The farthest objects we can observe emitted their light about 13.8 billion years ago, shortly after the Big Bang. But those objects are now about 46 billion light-years away because space has been expanding the whole time. The observable universe is therefore about 93 billion light-years in diameter. That's about 550 sextillion miles. Let me write that out. 550 followed by 21 zeros. A number so large that it's essentially meaningless to the human mind. We can write it down. We can do calculations with it. But we cannot truly comprehend what it represents. To sense this number, imagine every human who has ever lived, about 100 billion people across all of history. Now imagine each of those people lived a full 80-year life, one after another, in sequence. That's 8 trillion years of human existence, lived end to end. You'd need to stack about 70 million of those complete human timelines, 100 billion lives each, just to equal the time light would need to cross the observable universe. We're measuring in units our minds were never built to process. Within this observable universe are an estimated 2 trillion galaxies. Each galaxy contains billions or trillions of stars. If you multiply it out, the total number of stars in the observable universe is estimated at around 200 sextillion. That's a 2 followed by 23 zeros. More stars than grains of sand on all the beaches on Earth. More stars than seconds that have passed since the Big Bang. More stars than you could ever count. Even if you lived forever and counted 1 million stars per second. And we now know that most of these stars have planets. Based on data from the Kepler Space Telescope and other planet hunting missions, astronomers estimate that there's at least one planet for every star in the universe on average. Many stars have multiple planets, some have none. But when you account for all of them, there are probably as many planets in the observable universe as there are stars, perhaps more. That's 200 sextillion potential worlds. 200 sextillion possible places where life might exist, where civilizations might rise and fall, where beings might look up at their own night sky and wonder if anyone else is out there. The numbers are staggering beyond comprehension. The James Webb Space Telescope, which began operations in 2022, has already detected galaxies from very early in the universe's history. Some of these galaxies existed when the universe was only a few 100 million years old, less than 5% of its current age. We're seeing these galaxies as they were over 13 billion years ago, watching the universe in its infancy, when the first stars and galaxies were just beginning to form. The light from these ancient galaxies has been traveling for almost the entire history of the universe. When that light began its journey, there was no Earth, no star of ours, no Milky Way as we know it. The universe was young and chaotic, filled with hydrogen and helium gas collapsing into the first stars, some of which were hundreds of times more massive than our star is today. These first stars lived fast and died young, exploding as supernovae and seeding the universe with the heavier elements that would eventually make planets and life possible. The farthest thing we can see isn't a galaxy or a star, it's the cosmic microwave background, the afterglow of the Big Bang itself. In the early universe, everything was so hot and dense that matter and energy were essentially interchangeable. Atoms couldn't exist because the temperature was too high. Electrons couldn't bind to atomic nuclei. The universe was filled with a plasma, a soup of charged particles and radiation, all mixed together and interacting constantly. Then, about 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Electrons combined with nuclei to create hydrogen and helium atoms. This had a remarkable consequence. The radiation that had been constantly bouncing off all those charged particles was suddenly free. It could travel through space without being scattered or absorbed. That radiation has been traveling ever since, for 13.8 billion years. As space has expanded, the radiation has stretched along with it, its wavelength getting longer and longer, its temperature dropping from thousands of degrees to just 2.7 degrees above absolute zero. Today, we detect it as microwave radiation coming from every direction in the sky. When we observe the cosmic microwave background, we're seeing the universe as it was 380,000 years after the Big Bang. We're looking back in time to an era when the entire universe was a glowing fog, hotter than the surface of any star exists today. The patterns in the cosmic microwave background, tiny variations in temperature of just 1 part in 100,000, tell us about the structure of the early universe and have allowed us to calculate the age and composition of the cosmos with remarkable precision. The surface, where the cosmic microwave background originated, is called the surface of last scattering. It's about 46 billion light-years away from us now, at the edge of the observable universe. Beyond it, there's nothing we can see. Not because nothing exists there, but because the universe before that time was opaque. Light couldn't travel freely through it. It's as if there's a wall of fog surrounding us, and we can only see as far as the fog allows. What lies beyond the observable universe? This is one of the most profound questions in cosmology, and the honest answer is that we don't know for certain. Most cosmologists believe the universe extends far beyond what we can observe. The universe might be finite, but unbounded, like the surface of a sphere. You can travel forever on the surface of a sphere without reaching an edge. but the surface still has a finite area. Alternatively, the universe might be truly infinite, extending forever in all directions without limit. If the universe is infinite, then the observable universe is just a tiny bubble in an endless cosmic ocean. There would be other regions of space, separated from us by distances so vast that light from them will never reach us, containing other galaxies, other stars, perhaps other forms of life, all forever, beyond our ability to observe or contact. Some theories go even further. The concept of eternal inflation suggests that our entire universe might be just one bubble in an infinite foam of universes, each with potentially different physical laws. The multiverse, as this idea is called, remains highly speculative, but it's taken seriously by some cosmologists as a consequence of our best theories about the early universe. Whether the universe is finite or infinite, whether there's one universe or many, the observable universe is all we can ever directly experience. We're confined within our cosmic horizon, able to see only a limited bubble of existence, surrounded by vastness we can imagine but never explore. In 1998, two teams of astronomers made a shocking discovery. The expansion of the universe isn't slowing down, as most scientists had expected. It's speeding up. This accelerating expansion is driven by something called dark energy, a mysterious force that we don't understand, but that makes up about 68% of all the energy in the universe. Dark energy pushes space apart, fighting against gravity, and it's winning. As space expands, more dark energy comes into existence, which causes space to expand faster, which creates more dark energy, in a runaway process that will dominate the far future of the cosmos. The implications for the distant future are profound. In billions of years, the expansion of space will carry all other galaxies beyond our cosmic horizon. The Andromeda galaxy will merge with us first, and a few other nearby galaxies might be swept up as well. But eventually, everything else will be carried away by the expansion of space, moving away faster than light can ever bridge the gap. A civilization living in that far future would look up at the night sky and see only their own galaxy. They would have no way of knowing that other galaxies ever existed. The universe would appear to be a single island of stars in an otherwise empty void. The evidence that we take for granted today, the billions of galaxies visible in our telescopes, the cosmic microwave background, the expansion history of the universe, all of it would be invisible, carried beyond the cosmic horizon by the relentless expansion of space. We're living in a special time in the history of the universe. A time when we can still see enough of the cosmos to piece together its history and future. Future civilizations might not be so fortunate. The light that travels across these cosmic distances tells us not just about space, but about time. When we look at the moon, we see it as it was 1¼ seconds ago, our star 8 minutes ago, the nearest star 4 years ago, the center of our galaxy 26,000 years ago, the Andromeda galaxy 2.5 million years ago, the cosmic microwave background 13.8 billion years ago. The night sky is a time machine. Every direction we look, we're looking into the past. The farther we look, the further back we see. And the most distant light we can detect has been traveling for almost the entire history of the universe, showing us the cosmos as it was when it was young. Where are we in all of this? What is our address in the cosmos? You're on Earth, the third planet from our star. Earth is in the solar system, one star system among hundreds of billions in the Milky Way galaxy. The Milky Way is in the local group, a small collection of galaxies. The local group is in the Virgo supercluster. The Virgo supercluster is in the Laniakea supercluster. and Laniakea is one filament in the vast cosmic web that makes up the large-scale structure of the observable universe. If you could zoom out far enough to see the whole observable universe at once, Earth would be invisible. Our solar system would be invisible. Our galaxy would be a single point of light, one of 2 trillion points scattered across a sphere 93 billion light-years wide. We are small, unimaginably small. The entire history of human civilization, everything we've ever built, every war we've fought, every work of art we've created, every scientific discovery we've made, all of it has happened on a tiny planet orbiting an ordinary star in an unremarkable corner of one galaxy among trillions. From a cosmic perspective, nothing we do matters. The universe doesn't notice us. It doesn't care about our hopes and fears, our triumphs and tragedies. We're a brief flicker of consciousness in an almost empty cosmos, existing for an instant on the time scale of the universe. And yet, there's another way to look at this. We're here. We exist. We're made of atoms forged in the hearts of stars that exploded billions of years ago. Carbon from stellar cores, oxygen from supernova explosions, iron from the deaths of massive stars. We're literally made of stardust, the product of cosmic processes that have been operating for nearly 14 billion years. We're the universe's way of knowing itself. We're the cosmos looking back at itself, wondering about its own existence. In all the vast emptiness of space, in all the cold darkness between galaxies, on this one small world, matter has organized itself into forms that can think and feel and wonder. That's remarkable. That's extraordinary. That's worth something, regardless of how small we are. Given the vast scale of the universe, it seems almost impossible that we could be alone. 2 trillion galaxies, each with hundreds of billions of stars, many of those stars with planets. The numbers are staggering. If even a tiny fraction of planets developed life, if even a tiny fraction of that life became intelligent, the universe should be teeming with civilizations. And yet, we found no evidence of anyone else. No signals from distant worlds, no signs of alien technology, no visitors from the stars. The universe appears silent. This is called the Fermi paradox, after physicist Enrico Fermi, who famously asked, "Where is everybody?" The Fermi paradox has puzzled scientists and philosophers since Fermi posed the question during a lunch conversation in 1950. If the universe is so vast and so old, and if life and intelligence are even remotely common, then technologically advanced civilizations should have arisen millions or billions of years ago. Some of them should have spread throughout their galaxies. We should see evidence of them, even if that evidence is just the electromagnetic noise of their technology. But we don't. Despite decades of searching with increasingly sensitive equipment, despite scanning millions of stars for artificial radio signals, we've found nothing. The silence is deafening. The light year might be part of the answer. The distances between stars are so vast that they might represent fundamental barriers to contact. Our radio signals, which have been leaking into space for about a century, have now reached all stars within roughly 100 light-years. That sounds like a lot, but our galaxy is 100,000 light-years across. Our signals have covered a sphere 100 light-years in radius in a galaxy, 100,000 light-years across. That's a tiny fraction of our own galaxy, let alone the universe. Even those signals are getting weaker as they spread out. The farther they travel, the more they disperse, spreading their energy over a larger and larger sphere. By the time our television broadcasts reach a star a few dozen light-years away, they're so faint that they'd be almost impossible to detect above the background noise of space. Even with extremely sensitive equipment, Any alien civilization trying to detect us would need powerful radio telescopes pointed in our exact direction, at the right frequency, at the right time to pick up our signals. Even if we detected a signal from another civilization, communication would be painfully slow. A message to a civilization 50 light-years away would take 50 years to arrive. Their reply would take another 50 years to reach us. A single exchange of information would span a century. You could ask a question, and your great-grandchildren might receive the answer. This isn't a technological limitation that we might overcome with better engineering. It's a fundamental law of physics. Nothing travels faster than light, and light itself is incredibly slow on cosmic scales. The speed limit of the universe might condemn intelligent civilizations to eternal isolation, each one developing alone, asking questions alone, and eventually dying alone, never knowing if anyone else was out there. There are other possible explanations for the silence. Perhaps intelligent life is incredibly rare. The emergence of life from non-life might be a vanishingly unlikely event, something that happens only once in a trillion planets. Or perhaps the step from simple life to complex life is the hard part. Earth had single-celled organisms for billions of years before multicellular life appeared. The jump from bacteria to animals might be the truly difficult step, the filter that most life never passes through. Perhaps civilizations tend to destroy themselves before they can spread to the stars. We've had nuclear weapons for less than a century, and we've already come close to using them in devastating conflicts. Climate change threatens our planet's habitability. New technologies, from artificial intelligence to biotechnology, pose risks we're only beginning to understand. If most civilizations destroy themselves within a few centuries of developing advanced technology, that would explain why we don't see their signals. Or perhaps we're among the first. The universe is about 14 billion years old, but for most of that time, it may not have been suitable for complex life. The first generations of stars were made almost entirely of hydrogen and helium, the heavier elements needed for rocky planets and for life itself. Carbon, oxygen, nitrogen, iron were created in the cores of stars and scattered across space when those stars exploded. It took time for these elements to accumulate, time for rocky planets to form, time for life to evolve. Perhaps we're among the first civilizations to arise, early pioneers in a universe that will eventually be filled with intelligent life. Or perhaps we're genuinely alone. Perhaps the emergence of intelligent, technological life is so unlikely that it's happened only once in the observable universe, or only a handful of times, separated by distances so vast that contact is essentially impossible. We don't know. We may never know. But the search continues. Radio telescopes scan the skies for artificial signals. Space telescopes look for signs of life on distant planets. And with every discovery, we learn more about the universe and our place within it. What does the future hold? If we survive long enough, what will our descendants see when they look up at the sky? In about 5 billion years, our star will exhaust the hydrogen fuel in its core and begin to expand into a red giant. It will swell to about 200 times its current size, engulfing Mercury and Venus, and possibly Earth. Even if Earth isn't physically consumed, it will be scorched to a cinder, all water boiled away, all life extinguished. But that's 5 billion years from now. Humans have only existed for about 300,000 years. Civilization is only about 10,000 years old. 5 billion years is an almost inconceivable span of time. If humanity, or our descendants, survive even a fraction of that time, we could spread throughout the galaxy, perhaps even to other galaxies. Long before our star becomes a red giant, Earth will become uninhabitable due to gradually increasing stellar brightness. Our star has been getting about 1% brighter every 100 million years. In about 1 billion years, it will be bright enough to boil away Earth's oceans, ending life as we know it. This gives us 1 billion years to figure out how to survive beyond Earth, assuming we don't destroy ourselves first. In about 4.5 billion years, the Andromeda Galaxy will collide with the Milky Way. Over hundreds of millions of years, the two galaxies will merge, their stars mixing together like two swarms of fireflies passing through each other. The night sky will be transformed, filled with new stars and new structures as the combined galaxy settles into its final form. During the collision, the supermassive black holes at the centers of both galaxies will eventually spiral together and merge. This merger will release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time that will propagate across the universe. The final product will be a giant elliptical galaxy, lacking the spiral arms we see today, but containing all the stars of both original galaxies. In tens of billions of years, the accelerating expansion of the universe will carry all other galaxies beyond our cosmic horizon. The night sky will empty out, leaving only our local galaxy group, the merged remnants of the Milky Way and its neighbors, alone in an otherwise dark and empty universe. Imagine future astronomers living in that era. They would look out at the night sky and see only their own galaxy. All evidence of other galaxies would be gone, carried away by the expansion of space. The cosmic microwave background would have redshifted to such long wavelengths that it would be undetectable. These future astronomers would have no way of knowing that other galaxies ever existed. No way of deducing the expansion of the universe, no way of understanding the Big Bang or the true history of the cosmos. They would be intellectually isolated, trapped in an island universe with no evidence of anything beyond. We're living in a special time in the history of the universe, a time when we can still see enough of the cosmos to piece together its history and future. Future civilizations might not be so fortunate. The evidence that seems so clear to us now will eventually vanish, hidden beyond an ever-expanding cosmic horizon. In trillions of years, the last stars will burn out. The era of starlight will end, and the universe will enter a long, cold decline. Red dwarf stars, which burn their fuel most slowly, will be the last to go. But eventually even they will exhaust their hydrogen and fade away. Black holes will be the last large structures to remain. They'll slowly evaporate through a process called Hawking radiation, predicted by physicist Stephen Hawking in 1974. This radiation is incredibly slow. A black hole with the mass of our star would take about 10 to the power of 67 years to completely evaporate. That's a 1 followed by 67 zeros years. The current age of the universe, 14 billion years, is like the blink of an eye compared to this timescale. Eventually, even the protons and neutrons that make up ordinary matter might decay, leaving nothing but a thin soup of particles drifting through an ever-expanding void. The temperature of the universe will approach absolute zero. Time will stretch toward infinity, and in some sense, the story will be over. The far future of the universe is cold, dark, and lonely. But that's the far future. We're living in the bright morning of the cosmos, a time when stars still shine and galaxies still glow, and life still exists on at least one world. We're privileged to be here, to see the universe in its glory, to ask questions about our place in the cosmos. So what does the scale of the universe mean for us? How should we think about our place in this vast cosmos? Some people find the scale of the universe depressing. They look at the billions of light years of empty space, the trillions of galaxies beyond our reach, the fundamental isolation imposed by the speed of light, and they feel small and insignificant. I understand that reaction. When you truly contemplate how vast the universe is, when you really try to grasp what a light year means or how many stars exist in a typical galaxy, it can feel overwhelming. You can feel lost, adrift in an ocean of emptiness that doesn't notice you and doesn't care about your existence. But I think there's another way to see it. Yes, we're small. Yes, the universe is vast beyond comprehension. Yes, we're isolated on a tiny planet in a corner of one galaxy among trillions. But we're also here. We exist. We can look up at the sky and ask questions about what we see. We can build telescopes and send spacecraft and piece together the history of the universe from the light that reaches our eyes. Consider what a miracle that is. In all the vast emptiness of space on this one small world, matter has organized itself into forms that can think and wonder and love and create. Atoms that were forged in the cores of dying stars billions of years ago have somehow arranged themselves into beings that can understand their own origins. That's not insignificant. That's miraculous. We're the universe contemplating itself, made of stardust and capable of understanding the stars. We're the cosmos asking questions about its own existence. And, as far as we know, we might be the only ones doing this in our entire region of space. The scale of the universe puts our problems in perspective. The things that seem so important in our daily lives, the conflicts and anxieties and frustrations, they're all happening on one tiny planet. From a cosmic viewpoint, they're temporary and local. That doesn't mean they don't matter to us, but it can help to remember the larger context. When you're stressed about a deadline, or worried about a relationship, or anxious about the future, sometimes it helps to step outside and look up at the stars. Remember that you're standing on a small rock orbiting an ordinary star in a vast cosmos. Remember that the light entering your eyes has traveled for years or centuries to reach you. Remember that you're part of something far larger than yourself or your problems. The scale of the universe also reminds us of what we share. We're all on this planet together, all of us made of the same atoms, all of us looking up at the same stars. The borders we draw, the differences we emphasize, they seem less important when you realize we're all riding on a small rock through an enormous cosmos. We're not separate nations or tribes. We're one species on one world, with far more in common than different. We share the same sky. We share the same origin story, the Big Bang, the formation of stars, the creation of heavy elements, the birth of our solar system, the emergence of life on Earth. We're all cousins, all descended from the first life that arose on this planet billions of years ago. We're all made of atoms that were once inside stars. We're all, in the deepest sense, stardust looking up at the stars. There's something else to consider. If we're alone, or effectively alone because the distances to other civilizations are so vast, then we carry a unique responsibility. We might be the only minds in this region of the universe capable of understanding what we see. The only consciousness for light years in any direction that can contemplate the cosmos and appreciate its beauty. That makes what we do matter more, not less. Every scientific discovery we make might be unique in our corner of the universe. Every work of art we create might be the only art being created for trillions of miles around. Every act of kindness, every moment of love, every flash of insight might be precious precisely because they're rare, because they might not be happening anywhere else nearby. We didn't ask to be born into this situation. We didn't choose to exist on a planet isolated from other civilizations by light years of emptiness. But here we are, and we can decide what to do with the opportunity we've been given. We can explore, we can learn, we can build telescopes and spacecraft and send our eyes and ears out into the cosmos. We can try to answer the great questions. Are we alone? How did the universe begin? What is our ultimate fate? These questions may not have answers we can reach in our lifetimes, but the asking is worthwhile in itself. We can protect what we have. Earth is the only home we know, the only place where we're certain life exists. We should take care of it, preserve its biosphere, ensure that future generations can still look up at dark skies filled with stars. We can reach for the stars. Maybe not in our lifetimes, maybe not for many generations, but eventually, humans have always been explorers. We've crossed oceans, scaled mountains, reached the poles. We've walked on the moon. Eventually, we might reach other worlds, other star systems. The distances are vast, the challenge is enormous, but we've overcome enormous challenges before. Every time you look up at the night sky, you're participating in something ancient and profound. Humans have been looking at the stars for hundreds of thousands of years. We've told stories about them, navigated by them, wondered what they are and how far away they are. The curiosity you feel when you look at the stars is the same curiosity felt by your ancestors stretching back to the dawn of our species. And what you see when you look up is not just light, it's information. It's photons that have traveled for years or centuries or millennia to reach your eyes. Each point of light tells a story about a star that burned, about a galaxy that formed, about a universe that evolved over billions of years. You're connected to those distant objects across vast distances of space and time. The light entering your eye right now left its source years ago, in some cases billions of years ago. It's been traveling through the vacuum of space, crossing inconceivable distances just to end its journey by landing on your retina and triggering a signal in your brain. You're the end point of journeys that began before humans existed, before Earth existed, before our star existed. That's an incredible thing to be. You're a receiver, a sensor, a conscious endpoint for light that has traveled across the cosmos. And you're capable of understanding what you're seeing, of grasping the distances involved, of appreciating the scale of the universe that produced you. We've traveled from where you're sitting to the edge of the observable universe. We've seen the moon and our star, the planets and the stars, the galaxies and the cosmic web. We've talked about distances so vast, they defy comprehension, and timescales so long they dwarf all of human history. And at the end of it all, we're back here on Earth, on this small rocky planet orbiting an ordinary star, the only place in the universe we know for certain harbors life, the only world we've ever called home. The universe is vast and ancient and mostly empty. Stars are separated by light years of vacuum. Galaxies are separated by millions of light years of emptiness. The cosmic web stretches across billions of light years, but most of that space is void, dark and cold, and utterly lifeless as far as we know. And here we are. Conscious beings on a planet covered with water and air, warmed by a nearby star, protected by a magnetic field that shields us from deadly radiation. We won the cosmic lottery in ways we rarely appreciate. Against all odds, we exist. We're aware. We can look up and wonder, the true scale of the universe is beyond human comprehension. We can write the numbers, do the calculations, build models and simulations, but we cannot truly feel what a billion light years means. Yet we can try. We can stretch our minds toward the infinite. We can glimpse, if only briefly, the vastness that surrounds us. And in that glimpse, we can find something profound. Not just how small we are, but how remarkable it is that we exist at all. How extraordinary it is that the universe produced beings capable of contemplating its own existence. The universe doesn't need us. It existed for 13.8 billion years before we appeared and will continue for trillions of years after we're gone. But for this brief moment, on this small world, the universe has become aware of itself through us. And that's worth something. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, the next time you look up at the night sky, you're not just seeing points of light, you're seeing across light years. You're looking back in time. You're connecting with the universe in the most direct way possible. Photons from distant stars entering your eyes, ancient light telling stories of cosmic evolution. You're part of this universe, made of its atoms, living on its worlds, capable of understanding its structure and history. That's an incredible thing to be. Good night, and may you never look at the stars the same way again. Before we close, let me share some numbers that help define the scale of what we've discussed. These aren't meant to be memorized, but to give you reference points for the journey we've taken. The moon is 239,000 miles away. Light takes about 1.25 seconds to travel this distance. Our star is 93 million miles away. Light takes 8 minutes and 20 seconds. Neptune, the outermost planet, is about 2.8 billion miles from our star. Light takes about 4 hours to reach it. The Oort cloud extends to about 9.3 trillion miles from our star. Light takes over a year to reach its outer edges. Proxima Centauri, the nearest star, is about 25 trillion miles away. Light takes 4 years and 3 months. The center of the Milky Way is about 150,000 trillion miles away. Light takes 26,000 years. The Andromeda Galaxy is about 15 million trillion miles away. Light takes 2.5 million years. The edge of the observable universe is about 275 billion trillion miles away. Light from there has been traveling for 13.8 billion years, and those locations are now 46 billion light-years distant because of the expansion of space. These numbers stretch from the familiar to the incomprehensible, from distances you could walk to distances that dwarf all of human existence, from seconds to billions of years. That's the range of the universe. That's the scale we inhabit without usually realizing it. Let me take you on one more journey. This time, not outward into space, but backward into time. Right now, as you're listening to this, light is arriving at your eyes from all over the universe. Some of that light left the moon just over a second ago. Some left our star 8 minutes ago. Some left Proxima Centauri over 4 years ago. Some left the Andromeda Galaxy 2.5 million years ago. Let's follow that Andromeda light backward through time. 2.5 million years ago, that light left the Andromeda Galaxy. At that moment, on Earth, early human ancestors were just learning to use stone tools. Homo habilis, the first members of our genus, were emerging in Africa. The climate was changing. Forests were giving way to grasslands, and our ancestors were adapting to a new way of life. The light traveled through space, crossing the enormous void between galaxies. Millions of years passed on Earth. Species evolved and went extinct. Ice ages came and went. our ancestors spread across the world, developed language, created art, built civilizations, and all that time, the light from Andromeda was traveling toward us. 10,000 years ago, when the light was almost here, humans were inventing agriculture. The first permanent settlements were being built. Civilization, as we know it, was just beginning. 500 years ago, with the light just minutes away, Europeans were exploring the Americas. Leonardo da Vinci was painting the Mona Lisa. The modern world was taking shape. 50 years ago, with the light just milliseconds away, humans had just walked on the moon. The first personal computers were being developed. Your parents or grandparents were living their daily lives. And now, at this moment, after 2.5 million years of travel, that light enters your eye. The photons that left Andromeda when Homo habilis was chipping stone tools complete their journey by triggering chemical reactions in your retina. Information about a distant galaxy, preserved in light for millions of years, finally reaches a conscious mind capable of understanding what it represents. Every point of light in the night sky has a story like this. Every photon that reaches your eyes has traveled across vast distances and spans of time. You're the end point of billions of journeys, the receiver of ancient light, the conscious being who can appreciate what it all means. That's the true scale of the universe. Not just distance, but time. Not just space, but connection. Not just vastness, but meaning, created by minds that can comprehend their own place in the cosmos. We've come to the end of our exploration. We've traveled from your room to the edge of the observable universe, from seconds to billions of years, from distances you can walk to distances light takes billions of years to cross. Think about what we've covered tonight. We started with the familiar, the room you're sitting in, the neighborhood outside your window, the city that shapes your daily life. Then we reached the moon, 239,000 miles away, the farthest place any human has ever walked. We passed our star, that massive furnace that makes all life possible, sitting 93 million miles distant. We journeyed through the planets, each one a world unto itself, with its own mysteries and wonders. We left the solar system behind, crossing the vast emptiness that separates us from other stars. We discovered that even our nearest stellar neighbor, Proxima Centauri, sits over 25 trillion miles away, a distance so enormous that our fastest spacecraft would need tens of thousands of years to cross it. We explored our galaxy, the Milky Way, with its hundreds of billions of stars spread across 100,000 light-years. We met our nearest galactic neighbor Andromeda, rushing toward us across 2.5 million light-years of space. We climbed the hierarchy of cosmic structures, from galaxy groups to clusters to superclusters, watching the universe reveal itself as a vast web of matter and light stretching across billions of light-years. We reached the edge of the observable universe itself, that cosmic horizon beyond which we cannot see, and contemplated what might lie beyond in regions of space forever hidden from our view. The universe is vast beyond imagination. We're small beyond measure. And yet, here we are, conscious, curious, capable of understanding. Whatever your life holds, whatever challenges you face, whatever questions you're wrestling with, remember this: you're part of something enormous. You're made of atoms, forged in stars. You exist in a universe that's been evolving for nearly 14 billion years. And for this brief moment, on this small world, you have the privilege of being aware of it all. The universe doesn't owe us anything. It didn't create us for any purpose we can discern. We're accidents of physics and chemistry, results of processes that weren't aiming at anything, But we can make our own meaning. We can decide that it matters to be kind, to be curious, to take care of each other and our small planet. We can choose to look up at the stars with wonder rather than indifference. We can pass our knowledge to future generations who might one day reach destinations we can only dream about. That's the gift of consciousness. Not just to exist, but to choose what our existence means. Not just to see the universe, but to appreciate its beauty. Not just to understand the scale of the cosmos, but to find our place within it. The next time you look up at the night sky, remember what you've learned tonight. Those tiny points of light are distant suns, separated from you by distances measured in trillions of miles. That faint smudge in the constellation Andromeda is an entire galaxy of 1 trillion stars. And the light entering your eyes tonight began its journey before humans existed on Earth. You're seeing the universe as it was, not as it is. And that simple fact connects you to cosmic timescales beyond human comprehension. Thank you for taking this journey with me. If you've made it this far, I hope the universe looks different to you now than it did 2 hours ago. I hope the stars feel both more distant and more intimate, both more alien and more familiar. I hope you carry this perspective with you, not as a burden, but as a gift. A reminder of how extraordinary it is to be alive in a universe this vast. The cosmos awaits in all its terrible beauty and vast indifference, and you're part of it. Never forget that. Good night.